So the last section in our solutions chapter that we want to talk about are colligative properties. Colligative properties are a property of a solution that depends only on the number of dissolved particles in the solution, not on their identity of the particles. So colligative properties would include things like vapor pressure, the boiling point of a solution, the freezing point of solution, and whether or not osmosis or the movement of water is going to occur between a semi-permeable membrane. So in the case of vapor pressure is lower for a solution than for a pure solvent. So if you have dissolved particles in there, it's going to lower the vapor pressure of the solution. The boiling point is going to increase, however, for a solution than for a pure solvent. So if you dissolve particles in there, it's going to make it more difficult for the water to boil and change into a gas. The freezing point is also lower for a solution than for a pure solvent. And this is also important, especially in places that get a lot of snow, because what's commonly done is that you throw salt out onto the street. This is going to create colligative properties that are going to help lower the freezing point of that solution, in that case the water, so that you don't have ice forming as easily, right? So it's going to drop the freezing point of the water. And then osmosis is going to occur from an area that has a high water concentration to down its concentration gradient to an area of lower concentration. So it's going to move towards the solution that has higher dissolved particles in it than the other solution. So our vapor pressure is lower in solutions than in pure solvents. So what does this exactly mean? So our vapor pressure is depending on the equilibrium between the molecules entering and leaving the liquid surface. So if some solvent molecules are replaced by the solute particles, the rate of evaporation is going to decrease. So it's more difficult for evaporation to occur if you have more particles dissolved in the solution. That's why the vapor pressure of the solution is lower than that of the pure solvent. So it doesn't really matter what the identity of the solute particles is. That's irrelevant. Only the concentration matters, only the number of dissolved particles. So why does the boiling point increase in solutions? So it's very similar to the same reason why the vapor pressure goes down. Right? The boiling point of the solution is higher than that of the pure solvent because the solution has to be heated to a higher temperature for its vapor pressure to reach the atmospheric pressure. And that's because the number of particles that are actually in contact at the liquid gas interface is going to be lower for the solution than for the pure solvent because the solution has dissolved particles that will also be competing with the pure solvent with the solvent for the ability to be at that interface. So for each mole of solute particles, it's going to raise the boiling point of 1 kilogram of water by 0.51 degrees Celsius. So if you put salt, for example, in your water when you're going to boil pasta, it's going to increase the boiling rate of the water inside the pan and make the water boil at a higher temperature. So if you put 1 mole of glucose into water, it's going to raise the temperature by 0.51 degrees Celsius. However, if you put 1 mole of sodium chloride into that water, it's going to raise the boiling point of that solution by 1.02 degrees Celsius. It's going to double what you can do with 1 mole of glucose. Why is that? Glucose, we know, is a molecular compound. It does not break apart when it dissolves. So for 1 mole of glucose, you only have 1 mole of substance dissolving. However, the sodium chloride breaks apart into 2 components when it dissolves. The sodium is going to dissociate into the ion. The chlorine is going to dissociate into its ion, the chloride ion. So essentially, for every 1 mole of sodium chloride, you're going to have double the amount of particles floating around in the solution. And so that's going to increase that boiling point even further. So sodium chloride dissociates into the 2 particles and increases that boiling point further because, again, it doesn't matter what the particles are. It just matters how many of them there are in the solution for colligative properties. So you also get the freezing point depression of solution. So our freezing point of the solution is going to be lower than that of the pure solvent. And this is because our solute molecules, again, are going to be dispersed between the solvent molecules, and this makes it more difficult for the solvent molecules to organize into their ordered crystal lattice to form the solid form. So for each mole of non-volatile solute particles, the freezing point of 1 kilogram of water is going to be lowered by 1.86 degrees Celsius. So you can calculate how much you would need to add if you had a bunch of snow on the road to lower the freezing point of water, for example. That will end our section on solutions. So the things that you should know from this chapter: you should know what solutions are and what factors affect solubility. Mixtures are classified as either heterogeneous or homogeneous. Heterogeneous if the mixing is non-uniform. Homogeneous if the mixing is uniform. And we know the homogeneous mixtures can be further classified into, hopefully you said solutions or colloids. Solutions are going to be homogeneous mixtures that contain particles the size of ions or small molecules. So this would be below 2.0 nanometers in diameter. And our colloids are going to be between 2 and 500 nanometers. If you're above 500 nanometers, this is when you go to the heterogeneous mixture. The maximum amount of one substance, our solute, that can be dissolved in another solvent is called the substance's solubility. Substances tend to be mutually soluble when their intermolecular forces are similar. So this is our concept of like dissolves like. Polar dissolves polar. Nonpolar dissolves nonpolar. The solubility in water of a solid often increases with temperature, but the solubility of a gas within the solution is often going to decrease when you increase the temperature. So that's indirectly proportional. Pressure significantly affects gas solubilities, which are directly proportional to their partial pressure over the solution. Increase the pressure, you increase the solubility of the gas. Pressure does not affect the solubility of a solid or the solubility of a liquid, because those particles are already so close together that you can't push them together much closer by increasing the pressure. We talked about a lot of different ways that the concentration of a solution is expressed. It can be expressed by molarity. You should know how to calculate molarity. You should know how to calculate percent solutions. So you should be able to do percent weight by weight, or mass by mass, mass by volume, or volume by volume. You should also understand what parts per million and parts per billion are. We didn't talk about this concept in detail, but our osmolarity is used to express the total concentration of dissolved particles in a solution. And so we talked about this just a little bit when we were talking about our colligative properties. And we had that example of glucose and sodium chloride. Osmolarity refers to how many parts that something will actually dissolve into. So our sodium chloride, we might have a 1 molar solution, but the osmolarity would be 2, because the sodium and the chloride break apart into 2 ions when you dissolve that solution. So osmolarity essentially is used to express the total concentration of dissolved particles. So this could be a combination of ions and molecules. Our molarity expresses concentrations as the number of moles of solute per liter of solution. It's the most useful when calculating quantities of reactants or products because it's very specific. It's also probably the most difficult to calculate. You should also understand how dilutions are carried out. Note your M1V1 times M2V2, or you can have whatever concentrations you have. Concentration initial to the concentration of our dilutions. You should also understand what an electrolyte is. It's a substance that forms ions when dissolved in water and whose water solutions conduct an electric current. So these are called the electrolytes. Substances that ionize completely are strong electrolytes. Those that ionize partially are weak electrolytes, and those that do not ionize are non-electrolytes. Body fluids contain small amounts of these different electrolytes, and these concentrations are going to be expressed as moles of ionic charge or as equivalents, and typically, again, you'll see these as milliequivalents per liter. And then finally, you want to know how solutions differ from pure solvents in their behavior. These are the colligative properties. We talked about vapor pressure, we talked about boiling point, we talked about freezing point as our main colligative properties. And then these are just some key words that you should be familiar with from this chapter.